Okay, so part 3 of Riemann Sums, and like I said, I'm kind of doing all the information in 5.1 and 5.2. I just don't particularly like the way that Stewart sort of logically constructs everything. So I'm kind of going through it the way I believe is a more intuitive approach to Riemann Sums, and how all of this fits into the beginning of integration, integral calculus, and all sorts of fun stuff like that. So we're going to go ahead and do another example. And from here we're going to sort of launch off into not just finding it in terms of 4 subdivisions, but perhaps finding it in terms of 8, and finding it in terms of 16, and then finding it in terms of n subdivisions, okay? And we're actually going to be doing it in terms of sigma notation. So that's going to be sort of a reintroduction of that material a little more full force. We're going to be considering this function right here, which is an even function. It is a downward facing parabola with its vertex on the y-axis. I'll show you what it looks like. And we're going to be considering this function from 0 to 4, okay? And in the first iteration, we're going to go ahead and we're going to consider it for 4 subdivisions, okay? Now we know that we need to go I is equal to 1 to n of delta x and then f of x sub I, okay? That is basically the sigma notation in general. Now for this one, we happen to know that delta x, because it's b minus a over n, is just equal to 1. Okay, so delta x is going to be really, really easy for this particular one. Now, the shape and form of f of x sub I is going to depend upon whether it is a left-hand Riemann sum, a right-hand Riemann sum, or a midpoint Riemann sum. It usually winds up being a whole lot easier if we do a right-hand Riemann sum, okay? Because we're starting with 1. Because we start with 1, if we do a left-hand Riemann sum, we then have to sort of back it up to start at 0 and then progress forward. So for our purposes here, we're going to do a right-hand sum, okay? Now, what that means is that I know, because my n is equal to 4, I'm going from 1 to 4. My delta x is 1. And what I have here is I know that when I'm plugging it in, I'm going to, this x sub I is sort of stands in for the starting point of my x sub I is basically a plus delta x I, basically, okay? So what we need is basically, this is the starting place for the interval, and this takes you delta x past a I times, okay? And so if you were to plug in 1 and get x sub 1, it would be, in this case, since a is 0, it would be, so x sub 1 would be 0 plus 1 times 1, right? And x sub 2 would be 0 plus 1 times 2, okay? If x sub 3 is 0 and then 1 times 3, and x sub 4 is 0 plus 1, 4. So basically this is 1, 2, 3, 4, okay? Now I set it up so that it would be pretty easy. And so our x sub I, because I'm dealing with an interval that starts at 0, you're welcome, our a is 0, and really x sub I is just delta x times I. And if delta x is 1, then in this case, it's just I. So what we have is 6 minus 1/3 I squared. Okay? This is the particular form of this general form for this scenario. Okay? Now, this, you can do it by sigma formulas, and you need to reacquaint yourself with those. Or, you know, it just reminds us that we need to, this is 4 up here, minus 1/3 sigma I is equal to 1 to 4 of I squared. You need to remember that you can pull them apart like that. Now, what this means is that I'm adding 6 to itself 4 times, okay? And of course that winds up being 24. And this is 1/3. And remember that there's formulas for these, or you could just know that this is 1 squared plus 2 squared plus 3 squared plus 4 squared. Well, that's 1 plus 4 plus 9 plus 16, okay? And so 1 plus 4 plus 9 plus 16, this winds up being 17. This winds up being 13. So this right here is 30, okay? And if you want to do it again, just do it in order. 1 plus 4 is 5, plus 9 is 14, plus 16 is 30. So if we want to do this, that's divided by 3, so that's 10. So 24 minus 10 is 14, okay? That is the approximation of this function divided up into 4 subintervals on the intervals 0 to 4. That is the approximate area, okay? Now let's say we want a better approximation, because we know that a right-hand Riemann sum on something that is decreasing is going to be an underestimate. I know that 14 is too small, because all of the rectangles are going to fit inside of this area. So let's go ahead and do it for n is equal to 8, okay? So let's go ahead and kind of start over. So you have f of x is equal to 6 minus 1/3 x squared from 0 to 4, and we're going to do it for 8 subdivisions. Well, it's going to be a little bit trickier. My delta x changes because now I have 4 minus 0 over 8, and I know each subdivision is no longer 1 unit wide, but it is a half unit wide. Okay, we're still going to do a right-hand Riemann sum, and we need to go ahead and reconstruct the sigma such that it's 1 to 8. And then, of course, we need that delta x again, right? Well, delta x now is 1/2. Okay, and now my x sub I is, remember, a plus delta xi. Well, in this case now it's 0 plus 1/2 I. Or, you know, call it I over 2. I think that's probably a little bit easier. So we wind up getting 6 minus 1/3 I over 2 squared. All right. Now it's getting a little more complicated. The numbers are getting a little bit bigger, and so we're going to have to do a little bit more. It's going to be a little bit more burdensome, but it's not any more conceptually difficult to understand, right? This is the width. And you could, remember, you can take any constant and pull it out in front, okay? So we have this constant that's being multiplied, and if you pull it out in front, what you're really doing is you're factoring it out, right? Because what this sigma is the sum of 8 terms determined by this particular form. And if you pull the 1/2 out in front, you're just factoring the 1/2 out, and then of course you would just wind up multiplying it back across at a later time. Doesn't really matter, okay? Let's go ahead and simplify this just a little bit, okay? And let's do 1/2, 6 minus, well, if you square I over 2, that's I squared over 4. So that winds up being 1/12 I squared. Now here's the thing. Last time it was pretty easy. This time it's probably going to be a good idea to go ahead and use the formula. Now remember, if I have I is equal to 1 to n of I squared, okay, that's going to be n plus 1, 2n plus 1, all of that over 6. Okay. There's a formula for I, there's a formula for I squared, there's a formula for I cubed, and those need to be rememorized. There's also ones for I to the 4th and on up. I wouldn't really worry about those. So what we have here, I is equal to 1 to 8. And let's go ahead and distribute that 1/2 across here. We're going to get 3 minus 1/24 I squared, or sigma I is equal to 1 to 8 of 3 minus 1/24 sigma I is equal to 1 to 8 of I squared. Okay, well, this is obviously 24. Oh my gosh, that's the same as the last time. Okay, that's not a coincidence, by the way. Minus 1 over 24. Okay, now I need to plug 8 in for n. Okay, so it's 8 times 9 times 17 over 6. Well, I know that 24 is 8 times 3. So there's the 8, and I can take 3 out of the 9, and that cancels with the 24. I know that this 3 will cancel with the 3 inside of there, leaving 17 halves. So now I have 24 minus 17 halves, and that is my new approximation. Now remember, the approximation for 4 subintervals was 14. Okay, and it was an underestimate. So you'd think that a better approximation would be a little bit larger, and this is, okay, because that's 8.5 right there. So this winds up being 15.5 or 15.5. You know, as much as I love mixed numbers, just trying to get the actual idea of this general magnitude of it. Now, could I go through and do it for n is equal to 16? Well, I could. But why don't I try to do it for n is equal to n? Okay, so let's get the general idea of f of x is equal to 6 minus 1/3 x squared. I'm going from 0 to 4, and let's do it for n is equal to n. What's going to happen is at the end, I'm not going to get 14. I'm not going to get 15.5. I'm going to get some expression in terms of n. Okay? And what that will be is a function that describes the approximate area for this scenario for any value of n. So we know that it's sigma I is equal to 1, not to a particular number, but now to n. And now we know that delta x is 4 minus 0, not over a particular number, but over n, so that's 4 over n. I know that a plus delta xi is now going to be 0 plus 4 over n times I, okay, or, and of course that's your x sub I, right, or 4i over n. So we know that this sigma, I need a delta x and I need an f of x sub I. So delta x is 4 over n, and f of x sub I is 6 minus 1/3 4i over n squared. Okay? Now, I'm doing exactly the same thing I did for n is equal to 4 and n is equal to 8. I'm just doing it in the abstract for n is equal to n. Okay? I don't want to specify what my n value is. I want to have it in the abstract for any n value. Okay? So let's go ahead and here's the thing. Can I still take this delta x and pull it out in front if I want? The answer is yes. I can pull it out in front because, remember, this sigma notation is with respect to the variable I. So anything that is not I is a constant with respect to the sigma notation. Now, it isn't a constant just in general, but it's a constant with respect to the sigma notation, so it can be pulled out in front, okay? So let's go ahead and sort of running through this, simplifying it just a little bit, and I'm going to get 4 over n, and that's 6 minus, well, if I go ahead and square that, that's going to be 16i squared over n squared, or 16i squared over 3n squared, okay? And the hard part is remembering to square all three of these, the 4, the I, and the n, okay? That's where the careless mistakes will come in. And so I get 24 over n minus, okay, and that's going to be 64i squared over 3n squared. Now, I know that I can go ahead and pull this apart. And once I pull this apart, and I get 64 over 3n squared sigma I is equal to 1 to n of I squared. Okay? Once I've pulled that apart, I know that this right here is going to be n. I know that this right here is going to be that formula that I specified on the earlier one. So you get 24 over n times n, which is of course going to reduce to 24. Surprise, surprise. And this is going to be 64 over 3n squared times n plus 1 times 2n plus 1. All of that over 6. Okay? Now, these two cross out. That's easy to see. Now this n and one of these can cross out. Okay? Now 6 has a 2 inside of it, and so does 64. So that can be 32, and that can be transformed into 3. Okay? So what happens here is I get 24 minus 32 ninths, okay, because I'm just going to pull that out over here. And what happens here is I wind up getting, excuse me, oh, you know what I totally forgot? I actually made a mistake. Real quick fix. When I distributed, I forgot to add another one here. So this should be n cubed, okay? Sorry about that. That should be n cubed. So this is still squared. This is still squared right here. If you get down to here and you recognize the fact that this expression in here doesn't have the same degree in the numerator and the denominator, you've messed up somewhere, okay? Plus 3n plus 1 over n squared. Now here, what you know, I've simplified it all the way down to this, and that's just about as far as I can simplify it. We need to understand what this means. This is actually a function. This expression will give you the value of the approximate area under the curve for this function on this interval for any n. So if I were to want to plug in 4 right here, what do you expect I would get as a value? Well, I would get 14, okay? Because the only thing that's different is that instead of plugging in 4 at the beginning, like I did here, okay, on this first example that I did, instead of plugging in 4 at the beginning, I'm running it through with n and plugging 4 in at the end. Now, what do you suppose would happen if I plug in n is equal to 8? Well, I would get 15 and a half, because I would basically be plugging in the 8 after the fact instead of plugging in the 8 up here and basically having it embedded within my delta x and my x sub I. Okay? But the great thing about this down here is that if I'm asked for the approximation for multiple subintervals, say I'm given one scenario and I'm asked for 4 subintervals, for 8 subintervals, for 16 subintervals, I can actually just take this function right here, plug it into my calculator, and evaluate it at 4, 8, 16, and so forth, and actually get those values. Okay? And actually, let's go ahead and do that very quickly. Might run a little bit over our normal 20 minutes, but I think this is actually well worth it. So 2x squared plus 3x plus 1 over x squared. And unless I've made a mistake, okay, that is your y1. And I just have x's instead of whatever. Let's go ahead and insert, let's go ahead and just put in a insert parentheses, and we'll go ahead and run just to make sure that the notation's all nice according to the algorithm that it runs on. And so what we have here is we have a function. So we can go to the main screen and we can evaluate y1 at 4, and it's 14. We can evaluate y1 at 8, and it's it's 15 and a half. Okay, we can evaluate y1 at 16. Okay, and it would be an even better approximation. Okay, and here's what happens. What happens when I evaluate it for 1,000 subintervals? Well, when I get it to 1,000 subintervals, I'm getting really, really close to the actual value. And if you remember correctly, what we did with this s sub n is we then took the limit as n approaches infinity of s sub n, and we got not an approximate area, but the actual area. And in the next video, we will explore a couple of examples of that.